The primary hardware technology that we use on networks today is a standard called Ethernet. And Ethernet's absolutely fantastic for getting frames from one computer to the next, but it doesn't make a network. It doesn't provide resources. And that's what we need to talk about next. We need to talk about the network capabilities of your system to be able to do things like share resources, to access shared resources, and to be able to talk over all this plumbing to get the job done. So what I want to do, what I have right here is I've got a switch with a couple of connections to it. And this could be going to individual computers, basically making one simple broadcast domain. But I don't like this. You know what we need right now? I think we need more olives. So what I'm going to do, let's bring our olives back. And here's all my Ethernet cabling. And I guess we're going to need a couple of switches too. Delicious Ethernet switches. So let's just start off with 2 of these for right now. So what I want to do is I'm going to build a couple of broadcast domains very, very quickly. So what I'll do is we'll have each one of our switches has 4 connections on it. There's one. There's another one. Let's hook some computers to all this. These poor olives. And what I'm going to do is I'm going to create 2 broadcast domains. Now this is how networking started many, many years ago. The idea behind networking was that you would connect small groups of computers that were physically very, very close to each other together in order to get work done. Microsoft and a predecessor to them called Novell NetWare came up with the idea of what they called a local area network. A local area network is a number of computers that are physically connected to each other via a switch, and most importantly, are all part of the same broadcast domain. So let me finish this up here. Cream cheese, not even pimentos, really? Anyway, so what I have now right in front of me are 2 local area networks. They are 4 computers each, and they're hooked to a switch. Now back in the old days, no one ever thought about connecting these things. The idea is that you would have these 4 computers, and they would share stuff that computers that were close to each other would want to share. Microsoft's big push was 2 things: sharing folders and then also sharing printers. And that was really about all that there was to share. If the computers are physically close to each other, things like email and file transfer and stuff like that, which we use on the internet today, don't make sense because we're right next to each other. Put it on a floppy disk and hand it to the guy, kind of a thing. So that's how life started. Now, in order for these computers to talk to each other, all they have are MAC addresses. So what we need to do is, unless we want to sit here and access computers by MAC addresses, we need to come up with a naming system. And Microsoft used a networking protocol that they called NetBIOS NetBEUI that was designed to only do 2 things: share folders and printers. And you would type in the name of a computer, and you could give it a name like Mike's PC, and this one would be called Server 1, and that would be called Print Server, or whatever you wanted to call them. And as each computer booted up, it would begin broadcasting, saying its name and its MAC address. That way, all the other computers would write down, okay, so MAC address da-da-da-da-da is Mike's PC, and MAC address da-da-da-da-da is Server 1. And each computer would remember that. And as a result of that, we could get some pretty good networking done. But obviously, there was a lot of broadcasting being done. Now, imagine a world where we have not 2 local area networks, but what if we had, like, oh, I don't know, 300 million local area networks, which is probably a very, very low guess as to the number of local area networks on Earth today. And what if we want to start interconnecting them? Well, protocols with names like NetBIOS NetBEUI that use broadcasting as a way to have computers to talk to each other, they begin to fail really, really bad. We could, for example, and switches will let you do this all day long, you could interconnect 2 switches like this. What we've done now is we've created a very large broadcast domain of 8 computers. Now, let your imagination fly. Keep adding tomatoes in here and make more and more and more tomatoes until you get bazillions of interconnected tomatoes. The end result would be a network that would be so busy listening to broadcasts that you would never be able to get any work done. we had to come up with a better networking protocol, something that would separate the local area networks apart from each other, that would create an identifier for these different local area networks, and that was called TCP IP. TCP IP stands for Transmission Control Protocol / Internet Protocol. It's not one protocol, it's actually a bunch. So I've got two local area networks here. Now, what I'm going to do to make this work is I'm going to label this local area network over here, local area network, and this, I'm going to make something up. I'm going to call it network A, and I'm going to call this one network B. Now, in order to make now this would be a really bad network protocol because we could only have 26 networks, but for understanding how TCP IP works, this is a great place to start. So this is network A, and this is network B. So I'm going to name each one of these computers. Now keep in mind, Windows has to have a place for me to type this in. This is not like a MAC address, it's not burned in. So somewhere within the Windows interface, I'm going to have to type in on this computer that he's A.1, I guess, and he'll be A.2, and he'll be A.3, and he'll be, doesn't even have to be in order, he can be A.27, who cares? Over here, he'll be B.5, B.7, B.10, and B.22. Now the problem we have, though, is that switches don't know how to deal with these logical addresses. So we've got to add a new kind of box, something that doesn't look at MAC addresses, but rather looks at these new addresses, these logical addresses that we create. So what I propose we add is an apple. Well, in this case, actually, we're going to add a very special box, which we call a router. Routers don't care about MAC addresses. They only care about logical addresses. So I'm going to add this router, and we plug routers into switches. That's pretty much how we always do it. And now I've got this router box that is acting as an intermediary between these two local area networks. Now this changes things a little bit, because now, let's say I want to send let's say this is B1 right here. So B1 now wants to send a message all the way over to A3 on the other network. So what he'll create is something called a packet. The data is still in here, okay? But instead of having the MAC addresses, it uses the logical addresses. So we've got our data, our piece of our web page, or a piece of our printer document, or a Word document, or whatever it might be, email, who knows, who cares? But instead of addressing based on MAC addresses, it bases on logical addresses. Now, watch this very carefully. These are still Ethernet networks which still use MAC addresses, right? So what will happen is that, we'll say this is B1 right here. What he'll do is he will encapsulate his data into an Ethernet frame. And he's going to send it to the MAC address of right there. Routers always have two connections. So, and this is a regular network card going into this router, just like any other network card. It's got an IP, it's got a MAC address and everything. So it's going to go ahead and send it to the router. Now it goes into the router itself, and here's where the coolness happens. The router has a table that defines where all the networks are. And he knows anything going to network A has to be sent out this guy, and anybody going to network B has to be sent out this guy. So what the router does himself is he unpacks this, throws the Ethernet stuff away, and he comes in and he literally has to write very, very quickly a new Ethernet. Now I'm going to cheat. I'm not going to write out the MAC addresses, mainly because I'm lazy. But I'll write down something that looks halfway close. And he's going to recreate new Ethernet frames with legitimate MAC addresses. And routers do this on the fly. Notice this packet has never changed. The data inside is unchanged. The addressing has never changed. The router literally creates a new Ethernet frame and sends it over to the proper computer. The computer opens it up, checks the addresses, and it works beautifully. That's the idea of logical addressing. Now the trick with TCP IP is to appreciate that anybody who's seen a TCP IP address, they'll look like something like 192.168.4.55 or something like that. Now in my little demonstration, we only had one dot. Well, in the TCP IP world, we thought we were going to have a lot of these routers, and we had to create more granularity. Let me show you how all this works. In order to appreciate why TCP IP uses the numbering system that it does, you have to imagine the United States of America, because basically this is where it was invented. The idea behind TCP IP is that we were going to have routers, so I'm going to use these good old American nickels as representative of routers. That we'll have these routers that were going to be spaced all over the United States. And I want to put one in Boston, New York City. It's JPL. This is actually Rice University in Houston, Texas. Get one up in Washington there. And the idea that was for TCP IP to work was that these routers would be interconnected with high-speed, powerful lines. Routers have to have at least 2 connections, but they can have more. So in essence, what we're creating is a mesh topology of routers which can in turn interconnect multiple local area networks. Now this, what I'm drawing out right here, is the main, what we call the backbone of the internet. And the original concept is that these were going to be the main top routers of the internet. And I'm just drawing some arbitrary connections. Back then these were super high powered 56K lines and things like that. So anyway, there's some idea of how the connections might work. Now let's take a look at this for a minute. So this is what would be known as the backbone of the internet. And each one of these routers would be assigned a number. For example, this would be the 3 router, and this would be the 27 router. You could use any number between 0 and 255, not including 0 or 255. So 1 to 254. So this would be the 44 router. They never did this in order. You'd think they'd do 1, 2, 3, 4. They never did. And this could be the 210 router. So we have all these different routers that have one single number assigned to them. Now what I want to do is, let's go ahead and say, I forgot what I just said. Let's call him the 14 router. So let's zero in on the 14 router a little bit, and let's see what's happening in Houston, Texas. So I'm going to go ahead and I'm going to redesign my coffee beans on the fly. All right, so, and these are connections that this number 14 router has. However, if you keep looking at this for a minute, you have to appreciate that there's probably going to be other routers that are going to want to connect to that. So even though this is Rice University, here's the University of Houston, here's a couple of big oil companies, this is the local Texas Department of Transportation. Now these routers don't connect to the backbone, they only connect to this little router in Rice University. So what we're going to go ahead and give these guys their own little connections here too. There we go. So now these secondary routers, they're not connected to the main backbone, but they connect to a backbone router. So if this is the 14 router, the original idea would be that this router here would be 14.10, this would be 14.11, this one would be 14.12. You get the idea? So now if we zoom in one more time, so we're going to be here at University of Houston. Now if we go from University of Houston has a number of individual customers. I'm just going to put one in here for right now. And this is going to be the massive parallel processing department at University of Houston. And his little router is going to be 14.11. whatever 22 or something like that. And then from here, we'll hook individual computers and they'll put the last number will be for each one of those computers. So any computer hooked to here will be 14.11.22.5, 6, 7, whatever you might want to make it work out as. The whole reason that TCP IP has 3 dots in it is because when they originally developed the TCP IP protocol, they thought that you would never be more than 3 routers away from the top of the internet. Well, it didn't quite work out that way, and there's already replacements for the IP part of TCP IP, the addressing part. But for right now, we still work with IP addresses, and it's always going to be 4 values from 1 to 254 with 3 dots in between. Make sure you can recognize an IP address for the CompTIA exams.